All right. Let's take a look at situations with multiple objects. Um, this is it looks confusing, but it's really not that bad. Okay. It can be kind of daunting, but it's really not too bad. Okay. So we have three objects that are all attached by, so like we've got like a cord attaching one and two, a cord attaching three and four, and then you have a force pulling block three. Now, here's something important to consider is that when you're doing this, right, you are not, so like if this force right here is you pulling something, the train of blocks, then what's happening is you're not pulling all these blocks, you're just pulling M3. And then M3 is using the tension to pull M2, and M2 is using the tension to pull M1. So when you solve a problem like this, you actually have to break it up into systems, okay? My first system is going to be just M1, okay? So what I'm going to do is I'm going to put them in boxes. My second system is going to be M1 and M2, and then my final system is going to be all three of them. Okay, all three together. So here's what I'm going to do. Why am I breaking it up into systems? Well, here's what I'm going to do. Okay, I'm going to be able to make free body diagrams for all of these. So I'm going to focus on the biggest system first, which is all three of them. Okay, so what I'm basically doing is I'm condensing the entire system into a box. I'm putting the entire system into a box, and I'm ignoring any internal forces. What forces are internal to that box? Well, these two tensions are internal. That's what's holding the system together. Internal forces just mean what's holding the system together. Okay? So these right here, we don't even need to worry about the tension. So the forces that are acting on the system as a whole, okay, well, you obviously will have normal force, which I don't care about, mg, which, believe it or not, I don't care about. And it's not just mg, sorry, it's actually m1 plus m2 plus m3g, okay? And then you have a force this way, and that's just capital F. That's that force capital F that's pulling all the blocks, okay? So what you would do now, okay, is you'd have to understand, okay, that this right here, this force that's pulling, right, we can figure out the acceleration of the entire system. Okay? So what we can do is if we know this is our net force, just the F, capital F would be equal to m1 plus m2 plus m3, the total mass of the system, times a, the acceleration of the system. And it should make sense that the acceleration of the system should be the same for not only the whole system, but the same for each individual block. So the acceleration of the system should be the same as the acceleration of each individual block. So if the entire system moves at, what, 10 meters per second squared, then you would expect each individual block to actually move with that acceleration. And that should make sense because if you pull a train of blocks, they all should move together, right? Okay, so then I'm going to calculate, okay, the force that we've got is 30. The combined mass, 1 plus 2 plus 3 is 6. And then acceleration is a. We don't know what that is yet. Okay, so what I'm going to do to make life easy on myself, well, I mean, you don't even need to be a rocket scientist here. You can figure out what a is, and that's just going to be 5, right? 5 meters per second squared. So the acceleration of the entire system is 5 meters per second squared, and the acceleration of each individual block should also be 5 meters per second squared. Okay, let's look at the middle system, the red system. Okay, m1 plus m2. Okay, so I've got normal force going up, and again, I don't care about it. I've got mg going down. This is m1 plus m2. Okay, m1 plus m2g. Okay, and then I've got a tension force pulling to the right, because notice that in the red, right, the only force that's external to it directly is ft2. Okay. Okay, now we're looking at that. So again, what we would have to do is do our net force, right? Well, this is the only force that's acting on that system. So Ft2 would just be equal to ma. Okay, and in this case, it would be Ft2 equals m1 plus m2a. I keep messing that up there. Okay, and then we would actually have to calculate Ft2 is equal to the combined mass, which is 1 plus 2, it's 3. Okay, and then a, the acceleration, we already figured out was 5. Oh, 3 times 5, it's just going to be 15 newtons. Okay, look at that. And now you're laughing. Not literally. Okay, so then the last system is just M1 all by his lonesome. Okay, and that's got normal force okay, that's got mg, maybe just m1g, okay, and that's got the tension, what, ft1 on it, okay? It's the same darn thing. You just do ft1 equals ma, and then you figure out, okay, ft1 would be equal to the mass of 1, which is just 1, times the acceleration, which is 5. And then, oh, look at that. ft1 has to be 5 newtons, okay? See how that works out? Pretty straightforward. Now, this does change slightly if you have friction, just slightly, okay, just slightly. Again, I'm going to start with the whole system, okay, m1 plus m2 plus m3, okay. Again, you've got normal force going up, you've got this force F right here, you've got m1 plus m2 plus m3 times g, okay? And then you now have friction pulling back on it, okay? And the force of friction is actually going to change with the number of well, right, because the normal force is going to change, right? So what we would do is we could take F minus the force of friction, okay? F minus the force of friction, set that equal to m1 plus m2 plus m3a. Okay, that force is 30. Okay, the force of friction is mu mg. Okay, that should be m. Okay, mu mg, and we set that equal to the combined mass, which is 6 times a. Okay. Well, we need to figure out what mu times mg is going to be. Mu times m times g is going to be, and that's 30 minus mu is 0.2, so it's going to be 0.2 times m, which is 6, times g, which is 10. Okay, so that's 60, and then 0.2 times 60 is going to give us 12. Okay. Well, 30 minus 12 is 18, equals 6 times a, and that's going to give you 6, 12, 18, that's 3, right? Okay. So the acceleration of the whole system is 3 meters per second squared. And guess what? This makes the problem actually a lot more easy, right? To set up the next ones, right? All that you would have to do, I'm not going to show every single step here because I think it's pretty self-explanatory, okay? You get m1 plus m2, normal force going up, m1 plus m2 going down, times g, you have the ft2, and then you have the force of friction going behind. Okay, so when you set up your Newton's law equation, your Newton's second law equation, it would be ft2 minus the force of friction, okay, equals m1 plus m2 times g, or sorry, times a. Okay, times a. Okay. And you should be able to figure out that the ft2, right, is just going to be ft2 equals m1 plus m2a plus the force of friction, okay? And you would have to solve that whole thing out. I'm just setting it up for you right here, okay? And then the final system, just m1, okay? Again, normal force, mg going down, you have the T1, and then you have the force of friction going behind it, okay? You would do ft1 minus the force of friction equals m1 times a, and then again you would see that ft1 would be equal to m1 times a plus force of friction, okay? So then you would have to plug everything in to those equations and you could solve for the friction force. The friction force, just mind you, is not going to be the same for each system because there's less mass, which means less normal force. Okay. Okay. Atwood machines. Okay. You remember pulleys, right? Here's a generic pulley. Okay. Generic pulley system. Now it's important to remember, right, that if you let this system go, the heavier mass is going to accelerate downwards. Okay, so that's this one to the right. And so the lighter mass is going to accelerate upwards. Okay? Well, what forces are acting on this mass? You've just got tension going up, and then you've got mg going down. Okay? On the heavier mass, the acceleration is going down, and that means that mg is going, capital Mg, and then you have tension pulling up here. Okay? And the tension should be the same on both. Remember that an Atwood machine only seeks to change the direction of tension. It doesn't actually change the tension itself. Okay? So then we need to write an equation we need to write a Newton's second law equation for each individual mass. Starting out with the one in pink, right, little m, this is going to be little m, okay? The tension force is our forward force. Remember this notion of forward and backward forces. Forward force is what goes with the acceleration. Backward is what goes against. So the forward force in this case is the tension. That's going to go first, okay, minus mg, okay? That's the backwards force. And you set that equal to ma, okay? The larger mass, okay, I'm using like an exaggerated large M here. The forward force is capital Mg, and you subtract F sub t from that. Set that equal to capital M A. Okay. Pretty fun. And what you can do then is you can get an expression for the entire system for M plus capital M. Okay? And for the entire system, we're knocking out any of the internal forces. Okay? Those are internal. The tension's internal because it's bringing the system together. So then you see you're left with one force that goes with acceleration and one force that goes against. Okay? The capital Mg goes with acceleration and lowercase mg goes against it. So you would get capital Mg, okay, minus lowercase mg, and set that equal to the combined mass, big M plus little m, times A. Okay? And if you use this equation, you can actually solve for the acceleration of the system, which is the same as the acceleration of each individual block. And you get A equals capital M. So it should be capital M over, sorry, capital M G minus little mg over capital M plus little m. I don't know why I put the parentheses there. Okay? Okay, now what you would do, right? Then what you could do is you could take this expression that you just wrote and you would then be able to plug it back into either of these expressions to solve for the tension. In my opinion, I would like to use the pink one because tension isn't negative in this case. Okay? It isn't a backwards force in this case. Okay? So you could do whatever you want. You plug this expression in for that. Normally you would get this out to some value and then plug it back in as a value into those ones. That's perfectly fine. Okay? Okay, so what about this right here? The acceleration of the masses for the Atwood machine shown here. Now we actually have values for it. Okay. Well, the easy way to do this, okay, the easiest way to do this is you take the force on the system, okay, and set it equal to the mass, total for system times the acceleration of the system. Okay. Well, the net force on the system, right? If you take a look, you have tension up here, okay, Ft. You have, mg here. I'm going to call this big mg, and then you have little mg here, okay? Well, again, if we're talking about just the system, we can knock out the tension forces, and we're left with capital Mg and big mg, or little mg, right? And if the acceleration is going down, or up in the left mass's case, okay, then big mg is going to be our forward force, little mg is going to be our backwards force. So big mg, which is 90, okay, we subtract from that 60, because that's the other one, okay, and that should equal the total mass of the system. 9 plus 6 is 15, and then there's A, okay. You should end up with 30 30 equals 15a, so then a would have to be equal to 2 meters per second squared. Okay? How does this work out? Well, the 90 is the heavy mass, okay, which makes system go, okay, and then 60 is the lighter mass, okay, lighter mass uh, holds system back, okay, so lighter mass holds the system back, okay, okay. Now let's see what we can do. The last one is a weird case in where you actually have like two masses kind of strung together here, okay, with a tension between them. And the way that I am going to do this, right, is that if you look at the 6 kilogram, okay, you've got F tension going up this way. I'm going to call this FT1, the tension here, and it's going to be the same as the tension here, okay. Um, and let's see. So this is actually, fun fact, the exact same thing as the system before it. It's just instead that 9 kilogram mass has been broken up into a 7 and a 2. So the acceleration is actually going to be 2 meters per second squared, which is the same as the last. Same as last. Okay? Same as the last example. Okay? Now, we already know the acceleration. Okay? So what I'm going to do now is I need to figure out the tension force. Okay, I need to figure out the tension force that's on there. So I'm going to go with mg, okay, mg minus the tension force, okay, equals ma, okay? And again, so capital MG, we're basically considering these two together, right? That'd be 9D minus the tension force, which is going to be, FT is going to be, we don't know yet. And then we would do 9 times the acceleration, which was 2, okay? And you can figure out what the tension force is going to be from there. This is FT1, by the way, okay? And that would end up giving us 72 newtons. So we know that up here is 72 newtons, okay? Pulling upwards, okay? You can use either mass, okay? So what I'm going to do now is you can use either mass to get this, okay? It's perfectly fine. But then to get the FT2, okay, we're just looking at this system right here. We're looking at the 2 kilogram mass, okay? And so what we're going to do is we're going to look at, this is going to be mg, right? Because this part should accelerate down because it's heavier, right? So this one has mg going down, okay? And then, of course, tension going up. But it should be mg minus ft2, okay, equals ma. That's all you got to do for that, okay? Plug in your numbers. So the mass, since we're looking at just this really small 2 mass here, the mass is 2, g is 10 minus ft2, which we don't know yet. And then again, mass is 2. Acceleration we got earlier is 2, okay? So you get 20 minus ft2 equals 4. And then you should see that ft2 would end up being 16 newtons, okay? Okay. So we actually solved for both tensions there, okay? You can use either mass. It's, in my opinion, easiest to do with a 2 kilogram mass because it only has the tension force going up. It doesn't have to deal with mg and tension force going down. Okay. We already did that one. That was a different page. Okay. Here's a modified Atwood machine in where you have the blocks are horizontal now. Okay. Which is which is going to kind of affect some things a little bit. Now the table is frictionless, okay? So we're given that the little m is 8 kilograms, the big M is 12 kilograms. If it's frictionless, then what we should expect to happen is we should expect to see the acceleration. So right here, the hanging mass should accelerate down. That's the only way that makes sense. And this should accelerate to the right, okay? So what happens is when we draw our forces, right, we've got normal force going up, we've got mg going down, and the tension here, capital Mg, sorry. And then here we've got little mg going down and tension force going up. Okay? Okay, so I'm going to write an expression for, for both of them. Okay? I'm going to do for capital M. Here's my expression for capital M. Ft equals ma, right? Because for capital M, we only have tension force pulling in the right direction. Okay? For little m, I'm going to write mg minus the tension force, okay, equals ma, because little m is accelerating downwards, okay? And if I was to write an equation for the entire system, for m plus little m, okay, then what I would do is I would, of course, ignore the tension force. The forwards force is going to be mg, okay? And that would be it. It would literally just be little mg, okay? Little mg equals capital M plus little m a, okay? Because little mg is the only force that's actually pushing anything together, okay? Well, if you want to figure out what the acceleration is, you just got to divide both sides by capital M plus m, and you would get a equals mg over capital M plus little m, okay? Then you can calculate everything else out from there. If you calculate the whole thing out, you would do what is it? Okay, little mg, so this would be 80 on the top, and then capital M plus little m, that's going to be 20 on the bottom. So this would be 4. Okay, 4 meters per second squared. Okay. Once you've got 4 meters per second squared, then you can figure out what the tension is, okay, by taking this that you just solved and plugging it into there. And it's easiest, you can do either one, but it's easiest to do the top one. So you would just do Ft equals the little m, okay, which is 8, times the acceleration, which is 4, 8, 16, 24, 32. The tension should be 32 newtons, okay? So there you go. Now you have friction on the table, which does change things just slightly. Okay, big M is now going to have friction pulling back. It'll have normal force going up. It'll have mg going down, capital Mg. Okay, and then it has tension pulling to the right. This one down here, okay, little m has little mg going down and Ft going up. Okay. When I calculate it, when I start making my expressions, okay, capital M is Ft minus, okay, so capital M is Ft minus the force of friction, okay, equals capital Ma. And I'm actually going to write this out with the friction expression in there. So it should be Ft minus mu mg equals capital Ma. And then when I write my expression for little m, okay, I'm going to do little mg, okay, minus tension force equals little ma. So then when I write my full expression, okay, my complete expression for both of them, okay, the one for capital M and little m, okay, that's going to be my forward force. Okay, so acceleration is going down here, acceleration is going to the right here. Okay, so it would be little mg, okay. Oh gosh, I totally messed that up. Little mg, okay. And then now you do have a backwards force, which is minus mu mg, okay. So that would end up giving you, oh, and sorry, so you can set that equal to the combined mass, little m plus big M, okay, A, okay. So then you would solve for the acceleration, and the acceleration is going to be, oh gosh, what a huge mess right here. It's going to be mg minus mu mg over little m plus big M, okay. What a huge mess. And oh my gosh, I didn't even clarify the masses correctly. This is little m, this is going to be big M, okay. That looks kind of like another mu there. What a mess, okay. Okay. And then you would actually calculate that whole thing out. You can calculate that whole thing out, and you should just kind of check yourself. It would give you about 1 meter per second squared. Okay, kind of funny how it works out like that. And then you would then plug that into an equation to get the tension, and you can pick either one of these to do it from. I think, in my opinion, this top one's going to be easiest to do it from because you can do. In my opinion, it would be the top one right here would be easiest to do because then you just have to add this to the other side and you don't have to really deal with anything else. So then you would get Ft equals capital MA plus mu mg. Okay. And then if you calculate the whole thing out, right, you would get like what, 12 times the acceleration was 1 plus the coefficient is 0.5. Capital M is 12. G is 10. And when you calculate the whole thing out, you should end up getting about 72 newtons. Okay, which I remember that was like there's a solution in like a previous problem. Okay, but it wasn't the same one. Okay, that's for the horizontal one with friction. Now we need to look at the inclines. Okay, inclined outward machine is the last type of question that you can see. Okay, pertaining to outward machines. So when we have this, okay, the hanging mass is going to be the one that accelerates down. Okay, and the mass up here should accelerate up the plane. Okay, and what's going to happen is this is going to be hanging down capital MG. And then the vertical part is going to be, or the upward part is going to be Ft, tension, okay? For the block that's on the slope, okay, you have normal force coming out of the plane, okay? You have no friction, but you do have tension going this way, okay? And then you do have mg going straight down, and you should know that the components, okay? mg cosine theta, okay, and mg sine theta, okay. Okay, and by the way, this theta right here, it's not given to us in the problem, but this theta should actually be the 37 degrees from the previous part, which it didn't show, it doesn't show on there, it doesn't tell you, it should actually be 37 degrees. It's not like you have to solve for it, okay? To get a general form for the equation, right? So if I'm going to look at just big M, okay, if I'm looking at just at big M, then it's going to be capital Mg, okay, minus the tension force equals capital Ma. If I'm looking at just little m, okay, then it's going to be the forward force, tension force, Ft, okay, minus Mg sine theta equals little m a. And then if I do a combined equation for the two of them, if I do a combined expression for the whole system, capital M plus little m, okay, then it would be capital Mg, okay, minus little mg sine theta, okay, equals capital M plus little m a. There's your expression for that, okay? So now when I get a by itself, it's going to be this real kind of crazy looking expression, capital Mg minus little mg sine theta over capital M plus little m times, what the heck? Nope, I don't need the a right there, okay? There you go. Sorry, I got a little bit lost in the sauce when I was doing that, okay? Now, you can plug in the values yourself. You can rewrite the expression with all the values plugged in, but that's going to end up giving you 6 meters per second squared, okay? And once you've got 6 meters per second squared, then you can plug this back into either one of these expressions. You can plug it back into either one of these to get the tension force, okay? And you would solve for the tension where you could ultimately get the tension being equal to 120 newtons. Okay, so either way is perfectly fine. You just need to substitute this acceleration back into either one of the equations. And I'll tell you this, it's actually going to be easiest in this case to use probably the one in blue here, the capital M equation, because then you don't have to deal with any pesky signs. Okay, but either way works out just fine. You can do it either way. Okay, that saves you some time. Okay, now this one, now there's friction. Oh gosh, now there's friction. Okay, so and this isn't going to take too long either. I'm just going to show you how to get the expression. So capital M, right, has capital mg going down. It has tension force going up. The little m, okay, little m has normal force coming out of the plane. Okay, it has mg going straight down. Oh, that's what g with a really long tail. It has friction force going down the plane. Okay, and then it has tension force being pulled up this way. Okay. Now here's the thing that changes. Here's the thing that's kind of funky about this case is that the mg, right, is the two components. Okay. mg cosine theta, mg sine theta. Okay. There you go. There's your theta. Okay. Super sloppy, but I don't care. Okay. I'm tired. I want to go to bed. Okay. Capital M. Okay. For just capital M, it's going to be capital M G minus tension force, okay, set equal to capital M A. For the little m, okay, is going to be the tension force. Now, here's the thing. There's actually two opposing forces. There's friction and mg sine theta. This is going to be, so this is going to be, it's going to have mg sine theta. Okay, and now off to the side really quickly, I want to address this. Friction force is equal to mu times F sub n, right? Well, in this case, F sub n is not just mg. F sub n is actually the same as the cosine component right here. So F sub n is actually mg cosine theta. Okay, so now that I know that, here's what I need to do. I need to take this expression I just wrote and substitute it for normal force right here, and that gives me mu mg cosine theta. Okay, so that's what I'm going to do right up here. I'm going to substitute it into that expression right there. Okay, so then I need to subtract more friction force, which is mu mg cosine theta equals little ma. Oh gosh, that's a nightmare of an expression. Why would we ever do anything like this? Okay. And when you get the combined expression, capital M plus little m, right, for the whole system, okay, your forward force is capital mg, okay. Then your backwards forces, you have two backwards forces, m little mg sine theta, and the friction force mu little mg cosine theta, and we set that equal to capital M plus little m times a. And you can then figure out what the acceleration is from there, because that's going to be a ginormous mess, right? The acceleration would be equal to capital mg minus little mg sine theta minus mu mg cosine theta, okay? And you put the whole thing over capital M plus little m. Okay, boom, there you go. Then you would take this expression and plug it back into either one of these to get the actual tension. Okay. Oh my gosh, what a nightmare. And guess what? It's not even over yet because the last section is insane. Okay, peace out, Girl Scout.